Okay, I'm going to try and go through number 5 and then number 8 in this video. I did 6 and 7 earlier today in another video. Um, all right, so number 5 says starting from rest, a 5 kilogram box slides all the way down a frictionless incline from a vertical height of 10 meters. It travels a diagonal distance of 15 meters. What is the box's velocity at the bottom of the hill? So I've drawn a picture here. I've got my box at the top of this incline. It's starting from rest, okay? It's at a height of 10 meters, vertical height. They also give me a diagonal distance. I don't know if I need that or not, okay? And I want to know his velocity at the bottom of the hill. This is a situation where my acceleration would not be constant, maybe. You know, my box is probably going to be accelerating at different rates down the incline, possibly. But I don't have enough information to get acceleration anyway. So kinematics wouldn't be the way to do this problem. This is where conservation of energy problems can help us with certain quantities, because we can use that instead of like our equations, that we used at the beginning of the year to calculate for things like a velocity. So we want the velocity when it gets down here to the bottom, okay? So we're going to think about conservation of energy. This is a system, okay? It's isolated, so my initial energy should equal my final energy. And both of these buckets add up to a total value, right, which is going to be conserved. So one way that we'll move into writing this is my initial energies, the sum of them equal my final energies. It's really the same as what we've been talking about with our total mechanical energy. It's just reminding us that our total energy is conserved. Okay. So I've got gravitational potential. Okay. I don't have any kinetic at the top because it says that I started from rest. So all of my energy at the top is gravitational potential. And then I get to the bottom. Okay. At the bottom, I don't have any height. So I don't have any gravitational potential energy. All my energy is kinetic. So I'm setting gravitational potential, which is m times g times h, equal to kinetic final, which is 1/2 mv squared. I know m, I know h, I know like 9.8 and 1/2. Those are just constants. So I've got everything I need other than velocity. I can solve for velocity. Okay, so see how that's a lot simpler than trying to figure out how to use, do I have acceleration and time and displacement and all that stuff. You have a diagonal displacement, and so that might throw you off a bit, thinking I could use kinematics to solve this, but that's really unnecessary information that they give us, and sometimes they're going to do that, and you got to learn how to disregard that information. Oops, hang on one second. Okay, that took a while. It really wanted to turn the lights off on us. All right. So I'm going to figure out my initial gravitational potential. I've got my mass of 5 kilograms times 9.8 times 10 meters for my vertical height. Even though I'm sliding down this incline here, I'm at a height of 10 meters above the ground. And that's the height that I want to think about when I'm using my gravitational potential equation, because it's my height above the earth that gives me that potential energy. Okay. I'm going to set that equal to 1/2 times 5. Again, my mass times v squared. Simplify a little. I multiply all these out. I get 490. I multiply 1/2 and 5. I get 2.5. That's multiplied by v squared. Divide both sides by 2.5. I get 196. And that's not my last step. Remember, that's equal to v squared. I don't want that. I want v, so I've got to take the square root of both sides. And when I take the square root of 196, I end up with 14 meters per second. So that's how fast this box is going at the bottom of the hill. Okay. Okay, let's look at number 8. Hang on. Let me find my paper. Okay. Number 8's another one with an incline, so I figured those two kind of went together. And this is one that is an AP topic question. Okay, so we've got a 4-kilogram block. We're going to push it up an incline. The incline's at a 30-degree angle with the ground, or the horizontal. The box is pushed 5 meters up the incline, and then it remains at rest. So we want to know, what is the approximate change in the gravitational potential energy of the block and Earth system when the block is held at rest compared to its original location at the bottom of the incline? So how much did gravitational potential energy change from here to here? That's what that's really asking. And it tells us specifically, we're thinking about this block, we're thinking about the Earth, that is our system. This is our isolated system. So we're going to conserve energy. We only have to consider gravitational potential here because that's specifically what the question's asking about. So we know that we start off with the gravitational potential of 0 because my height here is at 0. And then our final, okay, is going to be whatever my value is up here at the top of this incline. So that's going to be the change between 0 and my final value. Okay, my change in my gravitational potential energy is that final because it went from 0 to this value. Okay. Now, in order to calculate this, I need mass. I've got mass is 4 kilograms. I need G, I already know that. And then I need H. They don't give me H specifically, but they give me enough information to get it. I got to use a trig function to get it. Okay. I know sine is opposite over adjacent, opposite over hypotenuse. So that's opposite. That's what I need because I want this height right here over 5 meters. They tell me 5 meters, so I know that's my hypotenuse. So I can use sine of 30 equals h over 5 and solve for h. End up with h is 5 times sine of 30. And when I do that, I should get 2.5 meters. Let's double check that. 5 times sine of 30 equals 2.5. Okay. So that's actually the height of my block once it's pushed all the way to the top of this incline and it's at rest up there. And that's where it's getting this gravitational potential energy from, is from that 2.5 meters above the earth or the ground. So then that makes my final gravitational potential. And because I started at 0, that is also the change in gravitational potential energy. My mass of 4 times 9.8 times my height of 2.5, I got 98, and they appeared to have rounded, so 100 joules is the answer I chose. Okay. All right, we got one more problem after this one.